Hi, everyone. I'm Joseph Mikael. I'm heading the quantum effort at EDF, and I recently took the charge of the Lab Quantique, so a French association that try to strengthen the ecosystem, the French ecosystem. So I wanted to take the opportunity today to give you an overview of the questions that we ask ourselves regarding quantum computing. So as everyone knows, we started our journey as teenagers, as enthusiastic teenagers, speaking about quantum supremacy, changing the world with quantum computing, and so on and so forth. Now we try to just count the euros that a quantum computer can bring to our businesses. And I describe that. So I speak about EDF Lab, why we started an effort in quantum computing. I speak about our vision of the quantum race that is going on right now. And at the end of my talk, I'll try to go beyond the qubit count. So, EDF has an integrated R&D division with €500 million per year of budget dedicated to the research around energy. So most of our job is to imagine the future of energy today, how we'll deliver energy in the next decade, within the next decade. And we have application almost everywhere, in every topic that you can imagine, except, of course, drug discovery. But apart from that, we have engineers working on mathematical finance, risk assessment, CFDs, PDEs, fluid dynamic mechanics, sociology, economy. So, of course, we could put quantum in most of these items that you see. We have a lot of partnerships with labs and startups and other big companies. And what's important in this slide is that we have a pair of high-performance computers, and we renew half of them every 2.5 years. So we have HPCs on-prem, and we buy them because they are full. So most of the time they are at 90% of charge. So it's not very advantageous to go to the cloud. So when we saw quantum arise in 2017, we asked ourselves what it could change for our businesses, of course. So we started an effort on quantum computing, and we are today 20 people involved in this team, not full-time, but still it's a big effort for our end user. Our goal is to clarify EDF strategy with regarding this new technology. One of the biggest goals that we have also is to build a skill of expertise. So quantum is a topic, of course, so it takes at least 2 years to train someone internally on this technology. So train in the sense, someone able to publish papers, so to be at the state of the art of the research. We want to position EDF as an end user able to use this technology when it will come up. Of course, so in the picture, of course, there's someone who is not in the team, you'll guess who. So, as I mentioned, we have quantum computing almost everywhere in our value chains. So from the left-hand side, we have application in material science, how batteries age with time, how our nuclear power plant age with time, safety risk assessment, which are combinatorial problems, partial differential equations, and CFD to simulate some mechanical behavior and some fluid dynamic around our wind farm, for example. And then you have all the family of topics around optimization, smart charging, planning, and optimal power flow, machine learning, of course. And the box, the green box at the bottom of the slide, have something which is sensors. So of course we have sensors in our power plant, and we ask ourselves what could sensor, what quantum sensor could bring to this to our power plant. So we have ideas around magnetometers, gravimeters, and radio frequency sensors. So we have a lot of ideas here, a lot of very nice opportunities. So it's not just about computing, it's also about sensing. So what's our view on the quantum race? So usually I used to present this slide to my management and to tell that this race is close to the end and so on. And you see some technology here, and the race represents which technology have the higher number of qubits. So of course you see supraconducting qubits, cold atoms that are winning the race. But to me the slide is not that good, because you don't know if one of the technology, including photons, topological qubits from Microsoft, spin qubits from Crowley or equal one, could be really fast from now to the end. So it doesn't represent the reality of the race. So I stopped presenting this slide internally, and I wanted to present something like that. Typical innovation curve that you learn in business school. So you have some innovation that goes linearly, which is the techno number 2. And you have some innovations that might face a long plateau before scaling. So it might be the case of Microsoft topological qubits. I don't want to tell you what's my mind on which technology is going on which innovation curve. But again, this slide to me is not good to present, because to us, finally, it's not a race at all as an end user. It should not be represented this way. For us, quantum computing, I tell that very, very clearly, is not existential. We won't change the way we produce energy with a quantum computer. But we have some opportunity in our value chain for some of the use cases that I represented before. We have some gains that we managed to, for which we managed to put some numbers, some euros. So we try to forecast ourselves, we try to project ourselves in how this technology would be used in our operational framework. So it's not about who would be the first to deliver 100 logical qubits. It's also how this 100 logical qubits will be integrated in our value chain. So let me give a couple of examples of that. So we started working, as Xavier presented before, on reservoir computing, and for some very specific situation and on some very specific data set, we managed to get an improvement of the performance of the algorithm, for the quantum algorithm, for a very niche application and very niche set of instances. So it's typically a quantum reservoir model. So Xavier presented that before. So it's very nice because you don't have to train it and so on and so forth. And so we ask ourselves, okay, it's good, but we will be able to use that in our operational framework. And we just try to put the time it would take to run that on a quantum computer versus the frequency of quantum computers. So I took a source. So of course, I didn't want to put which technologies has which frequency, because I don't want to enter into this debate. But you see that for some technology, it just won't be usable, because we use that online. We use that. We have to do a forecast every at least twice a day. So, for example, technology D and E won't be useful at all, even if there's any quantum advantage on the performance. So, just won't be usable at all. So you have to take that in mind. You have to have that in mind when you try to demonstrate, when you speak to your management. Another example, which is important to me, energy. So it's very hard to know the final electrical cost of these quantum computers. So I have a very large range from 5 kilowatts to 100 megawatts, and it's not a joke, 100 megawatts. And I think it's not an upper bound. So I think if you follow some curves, you'll have quantum computers which power is beyond 100 megawatts, so 10% of a nuclear power plant, which is not nothing. And it has to be integrated. I don't want to greenwash any. I don't want to do any greenwashing here, but if you are okay with that, you have to integrate this cost into your business model. So you have to buy, I don't know, a small SMR, or you have to buy to EDF a nuclear power plant, but you have to consider this cost. Okay. And so let me give you an example of an optimization problem, which is hard, known to be hard, which is a RCP-SP problem. So you have a planning problem. You have some sequence to respect. You don't want you need I don't know. You need Max to fix something after Bob did his job. So it's a typical optimization problem in which you try to reduce the number of days necessary to do the task. So here you see a 8-task problem, and the algorithm managed to do that in a couple of in a minimal number of days. So usually we are limited in the number of tasks that we manage to do on a classical computer, but I mean we have some kind of approximated algorithm. We know more or less our job, so we know how to deal with this planning manually with some expert knowledge, with kind of heuristics and so on. So if we manage to find an algorithm that help us reduce the number of days by 10%, you have to put that against the electrical cost to run the algorithm. So I just put here on this graph what it would take just to run one example of the algorithm. So the number represents some euros. And it's a question. So it's a question whether I would run an algorithm that would cost me, I don't know, 20,000 euros just for one answer. Today, we don't ask ourselves this question or HPC because it's kind of free. It costs a couple of cents, but not that much. It's not the same story for if you compare 20 cents against 20,000 euros, just to win one day of a planning problem. And I think I'm kind of optimistic here because I didn't enter the million and billion of shots necessary to qualify the algorithm. So the question of the electrical cost is not just for greenwashing. It's in an operational framework. It's very important. I don't have it. Finally, integrability is key. As I said before, we own HPC, we own our data centers, so we have to understand how this machine will integrate into our operational framework. If we need a stadium to welcome a quantum computer within our data center, it just won't work. If we need change all the infrastructure to to be able to input 100 megawatts into our data center, it just won't work. Today, we managed to, we have a power of 3 megawatts, but not that much. And we'd have to do a lot of works in order to increase the power that enter to our data centers. So, of course, carbon footprint are very important to us. And how these machines will integrate into our data centers is a very important question. Today you have technicians into our data centers. Would we need PhD in quantum physics to maintain the machine? And if so, yeah, we have to know. But I think it could be a problem for us. Finally, the technology itself has to integrate very well with our existing CPU, GPU, and whatever, because we need a strong integrability between the QPU and the classical computing power. So, as a takeaway, apart from the Quest ES, which subscription is about to open next week, which is a conference on December in Paris, EDF Paris. So it's my previous takeaway. My takeaway is that today we are as an end user, we are confident in the fact that we'll have 100 logical qubits by the end of the decade, which is amazing. We couldn't dream of that a couple of years ago. So, thanks to the efforts, thanks to the research, we will be there. Someone will be there. So today it's not a question of when to us. It's I think we'll have a quantum advantage somewhere in the decade. I don't know where. For very niche application, it won't be the big night, but for very niche application, we'll have some benefit from the technology. So to us, the main question is how this technology will integrate into our framework. And is it doable to integrate this kind of technology in our framework? So it's even more important to us than the number of qubits. With that, I'm done. So I think I have 2 minutes to take one question if needed.